In order to make sense of the upcoming section with electronegativity, we need to think back to some periodic patterns that are completely related to electronegativity that were encountered previously in Chapter 3. And I'll try to make a summary here, and I hope you find a periodic table to make this summary for yourselves. Where are atomic radii largest and smallest? Well, they're going to be smaller on the top of a group and larger at the bottom because there's more electron shells. More electron shells means larger radii. But that's for atomic radii. But within a certain period, they're also going to be getting smaller as you go across. So larger and smallest will be over on the right side. The smallest atomic radii are going to be on the top of the nonmetals in each of their groups. So atomic radii are smallest here. So smaller and smallest. Okay, keep that thought. Now, what about ionic radii? Ionic radii are a little bit different because they're going to be depending upon whether you've added or removed electrons. So ionic radii are going to be patterning how? Well, the smallest ionic radii are going to be at the top and on the left side of the periodic table, and the larger ionic radii, larger on the right in the nonmetals. If you go back to your notes from Chapter 3, you'll find that. But again, they're going to be larger as you go down due to the same factor in a particular group because of more electron shells. So that would be the ionic radii. Now, keep going. The other things to compare are ionization energies and electron affinities. So ionization energies are going to be how? Where do things lose electrons the easiest? So the smallest ionization energy is going to be at the left side on the metals. They're going to be larger ionization energies on the right because the metals will tend to lose electrons easily. That makes their ionization energy small. The nonmetals will not tend to lose electrons, makes their ionization energies large. Similarly, the electron affinities for metals versus nonmetals has a pattern. The ones that are the most likely to pick up electrons are on the right, so they're larger electron affinities. They're negative values for nonmetals, and they're going to be smaller for and/or the opposite sign. So smaller for the metals for electron affinity, and they're either going to be positive or zero, as in not much affinity for an electron at all. Where are things the most or least reactive? That's the next thing we need to pay attention to. And when end of Chapter 3, that was discussed. So the most reactive elements are at the bottom of groups 1A and 2A. And the ones that are most reactive in 7A are at the top. So fluorine and chlorine are more reactive than their cousins down the column. Cesium and barium are more reactive than their cousins above them in those alkali metals and alkaline earth metal groups. All right, so this relates then to where we're going next, is polar covalent bonds. Polar covalent bonds are something new because it has to do with something called electronegativity. So if we're talking about covalent bonds, there's shared pairs of electrons. That's the definition I want you to remember, is shared pairs of electrons. And if you have a polar bond, or sorry, a nonpolar covalent bond, the electrons are shared symmetrically, evenly, equally between two atoms. So if you have two similar atoms, like atoms such as two chlorines, you're going to have an exact equal distribution of electrons between the two atoms. But if you put chlorine with something else, like sodium, then we call it an ionic bond because the electrons are going to be taken and not shared. So taken by the chlorine, and sodium is going to lose electrons, lose an electron, and it gives you an ionic bond. And in this diagram, the side that has the most negative charge is going to be red, if the colors work for you, and the side that's most positive is going to be blue. Now, this is incorrectly shown. I need to give those as actual true charges, not partial charges. They're actual true charges. And the negative side is red, just like we suggested for ions. They're going to have plus and minus charges. All right, then. So how about what else can there be? Well, there are occasions where electrons are not shared equally between two atoms, and that's when we give this a term called the polar covalent bond. The two bonding electrons between a hydrogen and a chlorine in the HCl molecule are attracted more strongly by chlorine than hydrogen, which is why you get a redder color on the chlorine end of the molecule and a bluer color on the hydrogen end of the molecule. And so we're going to describe that as partially positive on the hydrogen side and partially negative on the chlorine side, because more electrons are going to be spending time, or more time by the electrons are going to be on the chlorine end of the molecule than the hydrogen end of the molecule. This is in contrast to the ionic bond, where the electrons were absolutely taken, not shared. So it's a true positive charge on the sodium end and a true negative charge on the chloride end. So sometimes electrons are going to be shared between atoms, but not shared equally. So the definition is as follows. Electronegativity is described as the ability of an atom in a molecule to attract the shared electrons in a covalent bond. Two examples are given here for the HF molecule and the HCl molecule with silly cartoons, but maybe they make the point. In the one on the left, you can get the idea that the fluorine is grabbing the electrons and pulling them away from this little hydrogen. You can barely see its symbol. And so the hydrogen's end is polarized. It's a polarized bond that more of the electrons are being held on the side towards fluorine. Similarly, in the HCl molecule, again, the hydrogen is very tiny and not very obvious. The electrons are shared, but not equally, and the majority of the electrons are being attracted to the chlorine in this molecule. So there is a spectrum of possibilities. They're seldom all black and white in these kinds of descriptions. There is such a thing as a nonpolar covalent bond, where things are exactly equally shared between two atoms. And then there's an ionic bond, where things are fully charged, fully positive and fully negative, with ions attracting one another between them. The polar covalent ones are the ones that are in between that we need to think about in this chapter. They have an unsymmetrical distribution of electrons, the bonding electrons, and they're going to be shown as dots. We're going to represent electrons with dots as we go, but they're attracted more strongly by one atom than the other. So we'll use these things that look like rainbow diagrams to you. They're electron density maps. They're describing, showing you which end is more negative and which end is more positive. But again, these, when it's polar covalent bonds, it's actual partial plus and partial minus, not true plus and true minus, because they're not ions. And where does electronegativity come from? It's a relative thing, and it's all related to fluorine, which has the highest electronegativity value. It's given a value of 4. You'll see the values in a minute. It's related to things we've already talked about. Electron affinity, the ability of electrons to be picked up by a particular atom. And those are measurable values. The chlorine has the highest measurable one. And it's also related to how, in other words, how chlorine picks up an electron and becomes a chloride ion. Of course, then it will also be related to other electron properties like ionization energy. So if it's a low ionization energy, the ability to lose an electron, it's also going to have a poor electronegativity as well. So for that reason, we can make some generalizations, and this is our next periodic trend, that the highest electronegativity values are in the top right corner of the periodic table, centered around fluorine, the highest. Notice that the red ones on this chart are the ones with the highest values. They're all nonmetals. The metalloids are somewhere in between, and the metals are all gray. And the halogen, or see, the noble gases aren't even included because they have no ability to be in a covalent bond. So we're going to want to remember that electronegativity, and I'm going to give it a symbol, it's much easier than writing the entire name, will be highest for atoms and elements that are including those ones from the top right corner of the periodic table. What else do we know from electronegativity? And how do we describe bonds using electronegativity values? We're going to be able to classify the bonds by the differences in the values that come from that chart. So for one example, if you have a difference of 0, no difference in how strongly an atom pulls on electrons in a covalent bond, there is a truly nonpolar covalent bond. If, on the other hand, if the electronegativity difference is large, such as greater than 2, then there's a lot of pull by one side than the other, more than one than the other, and we'll call that an ionic bond. So from this chart over here on the left, the electronegativity differences on the 2 to 3 side are going to be ionic, and the ones that are on the closer to 0 are going to be nonpolar. And there's a whole spectrum of possibilities for different compounds in between. Notice that the ionic ones are a lot of metals with nonmetals, and the covalent ones are going to be nonmetals. So the ones that are in the middle are between 0 and 2 somewhere, and this all a spectrum like that red and blue chart on a couple slides back suggested. Those are going to be the polar covalent bonds. So somewhere in the middle is going to be the polar ones, and their degrees of polarity. Some are more polar than others. So again, the metal and the nonmetal combinations are going to give you ionic bonds, and combinations of nonmetals give us the nonpolar. And the polar ones are somewhere in between, but mostly they're going to include nonmetals because covalent bonds occur with nonmetals. So as the difference in electronegativity increases, you go from covalent to where they share electrons equally to the difference in electronegativity is that, where they go from covalent to where they share the electrons completely to having a partial transfer of electrons when they're polar covalent to completely ionic when they transfer the electrons exactly from a metal to the nonmetal. Taken, not shared. All right, so what do we do with those? The bonds with when the bonds between atoms have an electronegativity difference greater than 2, we'll call them generally largely ionic. When they're less than 2, they're polar covalent. When they're very small, we're going to call them nonpolar. So let's look at some examples given some numbers. You can look them up on that chart, but they're provided on this slide for you. So if you have a molecule that contains 3 chlorines, a carbon, and a hydrogen, and we're going to look at the bond between the chlorine and the carbon, you look up their electronegativity values. So the carbon-chlorine bond difference is going to be 0.5, between 3.0 and 2.5. And again, that's a smallish value, so we're going to describe that value and compare it to the one in the sodium chloride. The sodium chloride has a difference of 3 versus 0.9 for the electronegativities, and that's much, much larger. So we're going to call the 0.5 difference between carbon and chlorine a polar covalent bond, and the larger one, greater than 2, between sodium and chloride, which you already should have guessed, is going to be ionic. So we can classify some other bonds, just do some more examples here, in these various compounds. Cesium chloride, hydrogen sulfide, we'll name that one in a little bit, later in the chapter, and then the bond between 2 nitrogens in this funny thing that's called hydrazine. You wouldn't know by its formula, but that's what that H2NNH2 means. So let's look at these things and think in terms of electronegativity values from the schematic diagram of the periodic table at the bottom. And remember that the highest ones are always in the top right, the lowest ones are on the left and lower parts of the periodic table. So for cesium chloride, what should we find? Cesium is a metal. It's at the lower end of the alkali metals, so it's going to be amongst the lowest possible electronegativity values. Chlorine is at the top right underneath fluorine, and so it's going to be a fairly high electronegativity value. The difference between the two is 2.3, and that would be an ionic bond. H2S, hydrogen sulfide. Hydrogen has a value of 2.1. You just have to look them up. We're not going to memorize the numbers in this class. And then sulfur, if you look it up on the chart, is 2.5. Oh, so the difference between those two comes out to be 0.4. Not huge, but not 0. And so we're going to call that polar covalent. There are greater and lesser degrees of polar covalent, but this one is on the low end of such things. If you compare then the nitrogen-nitrogen bond in the H2NNH2 molecule that is known as, I gave you a name, but I'll write it down, hydrazine. It's rocket fuel, kind of a fun, trivial thing to know. the bond in the middle of that between two nitrogens. Well, one nitrogen's value is going to be 3, and so is the other one. So the difference between them is obviously 0. So if there's no difference in electronegativity, we call that a nonpolar bond. And we call it strictly covalent. So if we look at another electron density map, electrostatic potential map, rainbow diagram, what do these symbols or colors indicate, and how do we understand them? The red end of the molecule is the part that has the most electrons, and so we describe that as being electron rich. And if this is water, well, that must be oxygen in the middle, and the other two would be the hydrogens. And so which one has the plus or minus, which one has the most electrons? The electron rich portion should be the negative end. That would be the oxygen. And which one is going to be electron rich is going to be the other end. So the hydrogen end in each case is electron rich. Does that make sense with electronegativity values? Yes. Oxygen should be a greater electronegativity compared to hydrogen. And so the electrons are going to spend more time on the oxygen end of the molecule than the opposite side. So one person whose name has been attached to the electronegativity discussions is Linus Pauling, who received Nobel Prizes in 2 different fields, which is unusual. And his statement is that electronegativity is a measure of an atom's attraction for electrons in a chemical bond. He has revolutionized the study of chemistry by building models of molecules, including things like proteins. But he was involved in the description of electronegativity. Okay, that would be enough of the discussion about electronegativity for this recording.